Is it visible?
Yes, ma'am.
Okay. Today in the morning session, we have started with design of beams, and we have seen some initial steps in the design of beams. That is how to decide the dimensions of the beam, that is the width, depth, and the span of the beam. Then we also see how to calculate the load acting on the beam. The load is considered from three different ways. One is from the slab, another is from wall, and the third is the self weight of the beam. Then we checked how to calculate the bending moment and shear force. That part actually you have already learned in MOS 1 and MOS 2. Then we seen the formula for calculation of area of the steel, AST formula. What are the limitations for that AST formula, minimum and maximum values. Then we also have seen how to provide the spacing between the two consecutive bars, reinforcing bars, and how to consider the cover to the these reinforcing bars. And the next part is the design of shear reinforcement. So design of shear reinforcement or design for shear is an integral part of design of beam. When you complete or when you design any particular beam, you have to have considered the design for shear also. Now, if you look into the syllabus, the design for shear is included in third unit. So I'm starting that part now from your third unit, that is design for shear reinforcement, because without design for shear reinforcement, the design of beam cannot be completed. So let us start with the design for shear reinforcement. I have included here some of the diagrams for the beams. You can see here the first diagram is for simply supported beam, which is subjected to central point load. And for this loading condition, what will be the maximum bending moment diagram and what will be the maximum shear force diagram? It is also drawn here. Similarly, if there is a cantilever beam subjected to point load at the free end, what will be the distribution of bending moment and shear forces? That is also drawn here. Similarly, we have considered here the fixed beam subjected to UDL as well as a continuous beam subjected to UDL. For all these different types of beams, how the shear force and bending moment varies along the span of the beam, all these diagrams are shown here. And I hope you are also aware of the various values of the maximum bending moment and maximum shear force when the different types of loadings are acting on different beams. Actually, I included these diagrams to just recall you that whenever we consider analysis of beam or whenever we want to design the beam, we do not design only it for flexure, but we need to design it for shear also. Because whenever there is a bending moment acting on the beam, the shear force will also be acting on the beam. So beam, though it is considered that it is majorly designed for flexure, we have to design it for shear also. Okay, so in IS 456, clause number 40, you have to refer for the design for shear. Okay, the earlier clause, that is clause 39, is related with design for flexure, in which you have all the clauses related to moment, related to design for a beam against the moment or bending moment. And clause number 40, you can refer the clauses for design for shear. Okay, so we will move to that clause later on. Let me go ahead for the next discussion now. Let us discuss now how the stresses vary along the cross section of any beam. I have drawn here a cross sectional view of a particular beam having a width B and overall depth D, and how the stresses in bending and stresses in shear varies across the cross section is shown here. So if you observe the first diagram, that is the bending stress distribution, we can observe here that the bending stresses are maximum near the extreme fiber of the section, and as we move towards the neutral axis, the bending stress goes on reducing. Along the neutral axis, the bending stress is considered zero, and again it goes on increasing as we move towards the another extreme fiber or bottom extreme fiber of the beam. If we come to the shear stress distribution, the shear stress distribution is little bit, or it is exactly opposite that of the bending stress. The shear stresses are zero at the extreme fibers, both top and bottom of the cross section. And as we move towards the neutral axis, the shear stresses goes on increasing. At the neutral axis, the shear stresses are maximum, And as we move again towards the bottom extreme fiber, the shear stresses goes on reducing and finally reaches to the zero. So if we consider any particular section, suppose if I'm considering any section in the tension zone of the beam, there will be certain amount of bending stress and certain amount of shear stress acting together in the beam. And for both these forces, we need to provide the design, or we need to consider some design aspects which will tackle both these stresses effectively. Okay, so now by considering the stress distribution diagram of bending and shear forces, let us come to the longitudinal view of the same beam. Let us consider a beam which is a simply supported beam and which is subjected to UDL. If I'm considering any particular element which is exactly at the neutral axis, which is shown here as number 1. Okay, so I'm considering first number of element which is along the neutral axis, how the stresses are acting on this element. Just now we have discussed about the stress distribution diagram for bending and shear across a cross section. So according to that, at the neutral axis, if we consider, the bending stresses are 0, whereas the shear stresses are maximum. So if I want to show the stresses acting on this element number 1, which is shown over here, it is subjected to pure shear because the bending stresses are 0 at the neutral axis and shear stresses are maximum. So along with this particular element 1, if I draw a free body diagram of this element, I can show here the shear stresses acting along this particular element. So if you consider the direction of the shear stresses, so it is exactly opposite on opposite faces. So if you consider these two components of the shear stresses, these two corners of the element, they will be under tension because the direction of the stresses are in this direction. So these two stress components will try to pull this particular corner away from the member. Similarly, this corner will also get pulled away from the member. So along this diagonal, if you consider, there is a tension. So in the opposite diagonal, there will be compression. If you try to pull, if you take a piece of any paper or any flexible material, and if you consider hold two corners, opposite corners in a hand, and if you stretch them, there will be a tension develop along that diagonal, and in the opposite diagonal, in the another diagonal direction, there will be the compression. So in this element, along this diagonal, there will be compression, and because of that excessive compression, a crack will get developed along this particular diagonal. Now if you consider this diagonal for this element, the crack will get developed at 45-degree angle. So whenever the cracks are developed in a beam at any particular region, which is subjected to pure shear, the cracks are normally developed at 45-degree angle. Now let us consider the another element which is denoted here by number 2. So I'm considering a second element over here. Now in this particular element is in a tension zone of the beam. Okay, now in tension zone at any particular section over here, as if we refer the earlier diagram, there are certain bending stresses as well as there are certain shear stresses. So for this element number 2, we can show both the stresses. Okay, so there are the shear stresses also, and there are some bending stresses also. Now, the combined effect of this shear stress and bending stress, when a crack will be formed, sorry, this diagram I have to refer, when a crack will be formed, the crack will not be at 45-degree angle because there is no any pure shear acting on that element, but there is, along with shear, there is some bending stress also acting on a element. So due to that, if you consider the diagram of element number 2, I have shown here the shear stresses also by tau and the bending stress also by F. So due to the combined effect of these stresses, the crack developed at this location in the beam will be having some angle between 45-degree and 90-degree. It will not be exactly 45-degree. It will not be exactly 90-degree. Why not 90-degree? 90-degree cracks will be developed only in the case when there is pure bending acting on that element. So if along this length of the beam, if I'm considering any particular element exactly at the center of the beam and at the bottom, extreme bottom fiber, where there is a maximum tension, Okay, and why I'm considering at the center? Because at the center of the span of the beam, there is a maximum bending moment and shear force will be 0. So if I consider any third element, say at this location, and if I want to show the stresses on that element, it will be only the bending stress. Shear stresses will be 0 in that case. And in that case, because of these horizontal stresses only, the crack will form in this vertical direction in that element. That is at 90 degree. So, any element inside a beam, when we consider subjected to stresses, we can consider three ways of stresses. One is pure shear, there are no bending stresses. Second is combination of shear and bending stress, and third is pure bending. So, if you consider the first case, that is pure shear, the cracks developed in the beam are normally run at a direction of 45 degree. When we consider the second case of combination of shear as well as bending, the cracks develop are not at 45 degree, not even at 90 degree, but the angle varies between 45 to 90 degree, any angle. And if you consider the third case, that is only bending, pure bending, the crack develop in the beam are at 90 degree. Okay, so by considering the combination of the stresses developed in the beam, whether it is shear stress, whether it is bending stress, or whether it is a combination of both these stress, normally we divide a beam into three different regions. Okay, so in this diagram, you can see there are three different regions shown. One, the region where there is a maximum bending moment, large moment, that region is called as a flexural region. Okay, because there is only the effect of bending stresses. In this region, as I discussed, the cracks developed in the beam are normally in the bottom portion, that is in the tension zone at the center of the entire beam, and the cracks develops are in vertical direction at 90 degree. Okay, now the second region is the one where there is a combination of both the stresses, shear as well as flexure. Okay, so there is certain amount of medium amount of shear force and medium amount of bending moment is also there. In this case, the cracks are developed at certain angle. Now these cracks are making some angle between 45 degree to 90 degree. Now the cracks which are developed in the middle portion, these are called as the flexure cracks. Okay, because these are developed only due to the bending action. The second region, in this region or even in this region, the cracks which are developed are because of the action of both bending as well as shear. So these cracks are called as flexure shear crack. These are called as flexure shear crack. And the third section, where there is a very small amount of movement, bending moment, and very large amount of shear. So there is a mistake in this diagram. There is no movement here. There is a large shear. See, if it is a continuous support, then definitely there is a large shear and large movement. But if the support is simple, as shown in another end, then there will be only shear force, maximum shear force. The bending moment will tend to 0 as we go close to the support. In this particular region, the cracks are developed mainly because of the action of shear force. And hence these cracks run diagonally along the beam, that is making 45-degree angle with the beam. So these cracks are called as web shear. Okay. Now, if you consider the shear due to shear, only pure shear, how the cracks are running, they are running at 45-degree angle. And to arrest these cracking, to avoid development of these cracks, we have to provide the additional shear reinforcement in the beam. Okay, see, there is a shear in this region also, along with movement. In this region also, at the center exactly the shear force is 0, but at in this particular region, as we go moving away from the center, the shear force will be there. The effect of shear force will also be there. So whatever the concrete present in the beam, whatever the main reinforcement present in the beam, they also take care of that additional shear or that shear forces along with the flexural stresses or bending stresses. But the force which is acting or the portion of the beam which is under pure action, pure shear action, for that many times we need to provide the additional shear reinforcement to avoid the development of these web shear crack, or which are also called as the diagonal tensile crack. Okay, so to avoid these cracks, we need to provide the shear reinforcement, and that shear reinforcement is provided in the form of a vertical reinforcing bars. Okay, up till now you have learned about that we are providing a reinforcement in the tension zone of the beam which run parallel to the length of the beam. But there are some steel which is provided perpendicular to that steel, and that perpendicular steel is called as shear reinforcement, or in practical language it is called as stirrups. Is it clear the concept of shear up till now, whatever we have discussed? Students?
Yes, ma'am.
Okay. So now let us see how the shear transfer mechanism takes place. This is a particular section taken for a beam. This is a beam in which a certain amount of main reinforcing steel is also provided and concrete is also provided. So how the entire shear force acting on a beam is transferred in the beam is that diagram is through this diagram it is explained. So the shear force is registered by various mechanisms, or there are four different mechanisms considered in this. The first is the shear resistance shown by the concrete itself. So whatever the shear force acting on a beam, some component of that shear force will be resisted by the concrete. Okay, so that is the shear resistance shown by the concrete itself. Then the remaining amount of shear, out of that a certain or the vertical, especially the vertical component of that remaining force is resisted by the interface shear, or that force is called as interface shear, and it is resisted by the aggregate interlock. See, when we deal with a concrete is a heterogeneous mixture of aggregates and cement and fine aggregate. So it is basically a mixture of aggregate and fine matrix. And there must be some interlocking between the aggregate and fine matrix. And because of that interlocking, what some amount of shear acting on a beam will get resisted by the interlock, aggregate interlock. And that vertical component, if I will consider this as a shear force, total shear force VA, which is interface shear force, that its vertical component will be resisted by the aggregate interlock. Its horizontal component VAX up to certain extent and the VD in the tension zone, it will be resisted by a dowel action. Now, what is the dowel action? There is a tensile force present in the tension reinforcement which we have provided in the tension zone of the beam. Vertical component of that tensile force present in the steel that also has a certain shear carrying capacity, and because of and that vertical component is called as dowel force in the tension reinforcement, and that dowel force take cares about the remaining shear component in the beam. So if you consider first three mechanism, the total shear force, some component of that is resisted by concrete, then some component is resisted by aggregate interlock, and some component is resisted by the dowel action. Remaining shear resistance is to be carried out by shear reinforcement. Okay, so whatever is the remaining shear force in the beam, that should be carried out safely by the beam, and for that we need to design the shear reinforcement, which is called as the transverse reinforcement. Now the transverse reinforcement is provided in three different ways in the beam. First is either by providing a vertical stirrups. These are called as stirrups. So if you look into this diagram, this is the cross-sectional view of actually the longitudinal view of the beam, in which the main reinforcement in the bottom and top portion of the concrete is shown, and some vertical bars are shown. These vertical bars are nothing but your vertical reinforcement, which are called as vertical stirrups. So the stirrups are provided either in the vertical form, or these may be provided in the inclined format. Why inclined? Because the cracks develop in the beam because of these shear are at 45 degrees, so in the inclined position. So sometimes instead of providing the stirrups in a vertical direction, these are also provided in the inclined direction, which are called as inclined stirrups. And sometimes the combination of both is considered, that is vertical stirrups, the combination of vertical stirrups with bent up bars or inclined shear with bent up bar, that combination is considered. So if you consider this first diagram, this is actually the combination of both. That is, the bars are bent here, The main reinforcement steel is bent up and the vertical stirrups are also provided. So this is the combination of vertical stirrup with bent up bars. Okay. Now, if you consider this second diagram, the second diagram represents the number of legs in the stirrup. Number of legs means suppose this is a cross-sectional view of a beam and there are four longitudinal reinforcement and the vertical stirrups are tied around these four bars in this fashion. So this is a single legged stirrups. Okay, or sorry, not single leg, it is called as two leg stirrups because there are one and two legs. Okay, so this is called as two leg stirrups. Now sometimes we have to provide the multi-leg stirrups like this as shown in this diagram. So for this case we need to provide minimum four tensile reinforcement or four bars at the bottom and at the top also, so that the inner two at the bottom and two at the top, they will be tied together by one vertical stirrup, one square, I mean to say, and the outer can be considered by the another square. So this is a multi-legged or four-legged stirrups. Okay, is it clear about the types of shear reinforcement? The shear reinforcement is provided either in the form of vertical stirrups or inclined stirrups or the combination of vertical and bent up bars. Is it clear, guys, the concept of shear force and why we need to design for the shear reinforcement? In the beam, we have to always design shear reinforcement, but depending upon how much shear force is acting on a beam, according to that, we have to decide whether we need to provide the additional shear reinforcement in the form of stirrups and bent up bars, or there is no need to provide the additional separate design shear reinforcement. The minimum shear reinforcement, whatever is suggested by the code, whether it is sufficient or not, that also we need to check in the design steps. So is it clear to everybody? Any doubts in this?
Ma'am, where do we use that multi-legged stirrups?
See, if the number of bars are more on in a beam, number of bars means the main reinforcement provided are more, and also the shear force is more. The amount of force acting on a beam is also more. In that case, we have to go for a multi-legged stirrups. See, when we provide the shear reinforcement, it also provides a certain type of confinement because we are tying all those bars together with the help of these shear reinforcement. So it has a dual function. So it confines the concrete, the main reinforcement, as well as it provides a resistance towards the shear force.
Okay.
Is it clear? Huh? Okay. All right. So let us move to the design steps now. We will discuss all these design steps today and then we'll form the problems based on the same we will consider in the next lecture. Okay. Uh, the first step is we have to calculate the design shear force and how to calculate the force, the load because of which the design force will be there on the beam, that we have discussed in morning lecture. So first step is calculate design shear force, which is denoted by VU. Then second step is calculate maximum allowable shear in a concrete. In concrete, what is the maximum shear which is allowed to be developed? That we have to calculate. For that, the formula is, it is denoted by VUC max and the formula is tau C max into BD, where tau C max is the maximum shear stress, B is the width of the beam. If we are designing flange beam, then it will be BW, and D is the effective depth of the beam. Now, what is tau C max and what are the values of this tau C max? It is given in table 20, page number 73. So now all of you just open the IS 456 and also open page number 72, clause number 40. I hope everybody is having a soft copy of code or hard copy of code. Everybody open page number 72 and clause number 40. Okay, so clause number 40 discusses about the limit state of collapse for shear, and all the various formulas which we will require, all the values in the tabular form, whatever we require will be available in clause number 40. Now we were talking about the maximum allowable shear force in the shear stress in the concrete, and for that we require the tau c max value, which is given in table 20 here. Okay, so if you observe table 20, the maximum shear stress given are dependent on the grade of the concrete. Okay, so the shear transfer mechanism, whatever we have discussed earlier, just 5 minutes before, that the shear is resisted by the concrete, it is resisted by the aggregate interlock, by the dowel action of the reinforcement. So if we consider all these effects, so if we consider the concrete, then we have to deal with the compressive strength of concrete. So FCK will be there in the formula. Then aggregate interface, we have to consider size of aggregate. Then dowel action, we have to consider grade of steel. So all these parameters are having a direct impact on shear resistance calculations. Okay, so this is table 20, in which we can find out the maximum shear stress tau c max, which is required for the calculation of maximum allowable shear in the concrete. Okay, then once we calculate the VUC max, we have to compare it with VU. VU means the total shear force acting on a beam. VUC max, that is the maximum allowable shear in a concrete, should be always less than VU. If not, see, whatever the calculated VOC max, if it is coming less than VU, it is okay. If not, if it is exceeding VU, then we need to resize the section. That is, whatever is the dimension of the section we have decided earlier in the first step of the design of beam, that we need to design again. Design again means we have to increase the dimension of the beam. Okay, or if there are restrictions for the dimensions of the beam, in that case we can even change the grade of the concrete, because as we have seen table 20, the tau c max depends on the grade of the concrete also. So we can go to the higher values of the grade of the concrete in the design. Anyways, whether you are changing the size of the section or grade of the concrete, all the calculations you need to repeat again, right from the first step for the design of beam, because if you are changing the size, it means you are increasing the width and increasing the overall depth. So all other calculations will change accordingly. If you are changing the grade of the concrete, then FCK value will change. So all calculations will again ultimately change. Okay, so design of shear reinforcement, this is the second important step. Then the third step is we have to calculate the shear force resisted by concrete. Now, as again, whatever the shear transfer mechanism we have discussed, according to that, what is the component of the shear which is resisted by the concrete, that we are calculating here. So that is calculated by using a same formula again, but instead of using a maximum values, we have to consider the design values here. That is, VUC is equal to tau c into BD, where tau c is the design shear strength of the concrete. And these values are given in table 19, page number 73 of IS 456. So if I will go back on page number 73, this is page number 73, table 19. Okay, so it gives us design shear strength of the concrete, tau c, which depends on again the grade of the concrete. And if you observe this formula, 100 into AS upon BD, that is the percentage of steel provided in the beam. So the design shear strength of concrete depends on two parameters: concrete grade and the percentage of steel provided in the beam. Okay, so that's why we have to first calculate the AST, and then we have to come to the design of shear reinforcement. Okay, then we have to calculate next, that is the shear to be resisted by shear reinforcement. See, we have the total shear force VU, and we have calculated VUC, that is the shear force resisted by the concrete. Now we have to find out what is the shear resisted by the reinforcement, shear reinforcement. So it is simply total shear force minus the shear force resisted by the concrete. It will give me the total shear resisted by the shear reinforcement. Now, this total force, which is to be resisted by the reinforcement, shear reinforcement, it is again considered or divided into two different parts. One is the force which is resisted by the bent up bars, and another is the force which is resisted by the minimum shear reinforcement that we have to provide compulsory in every beam. Okay, so the next step we need to calculate these forces. That is, this total VUS will be the combination of these two forces, VUSV and VUSB. VUSV minimum means the shear force resisted by minimum shear reinforcement, and it is given by the formula 0.4 BD. That formula is given in clause 26516, page number 48. So I will go to page number 48 now. I hope everybody is looking into the code. Huh? Page number 48. Okay. Here comes page number 48. This is the formula for minimum shear reinforcement. Okay, 26516. Minimum shear reinforcement in the form of stirrup shall be provided such that ASV upon BSV is greater than or equal to 0.4 upon 0.87 FY. So what is the formula for minimum shear reinforcement? It is given over here as 0.4 BD. Okay, where is that formula? 0.4 BD, minimum value. Wait, 0.4 BD. Okay, this one 0.4 BD. The D is not here. 15%. No. This is the formula actually, which is a combination of both grade effect of grade of steel as well as the size dimension of the beam. Okay, then what is next? Shear force resisted by the bent up bars. Okay, VUSB. So its formula is 0.87 Fy ASV into sine alpha, clause 40.4 C part, page number 73. So I will go to page number 73 again here. Oh, 73. Okay, here is the formula. I will go here, designed for shear reinforcement, bent up bars along with stirrups, and this one is only for inclined stirrups. So what we were calculating here, calculate shear force resisted by bent up bars. So this is for bent up bars. For single bar or single group of parallel bars all bent up at the same cross section, VUS is given as 0.87 Fy ASV into sine alpha. Okay, this is the formula to find out the shear force resisted by bent up bars. Okay, so VUSB is calculated. Now there are limitations for this VUSB. It should be less than VUS by 2. It means whatever is the total shear resisted by the shear reinforcement, half of that should be resisted by the bent up bar, and remaining half, for that either we have to provide the minimum shear reinforcement or we need to design the additional shear reinforcement. Okay, so let us consider now the next step, that is if VUC, that is the shear force resisted by concrete, plus VUSV minimum, shear force resisted by minimum reinforcement, plus VUSB, shear force resisted by bent up bars. All these three shear forces, if it is greater than or equal to VU is the actual force, shear force acting on a beam. If the shear resistance provided by concrete, minimum reinforcement and bent up bar, it is greater than the actual force acting on the beam, there is no need to design for stirrups. We have to provide the minimum shear reinforcement only. And that minimum shear reinforcement is given by VUSV minimum as per this formula, 0.4 BD. Okay. Now, if this addition is coming less than VU, then we need to provide the design shear reinforcement. And that design shear reinforcement is designed for VUSV value, how it is calculated. So total shear force minus addition of all these, that is minus VUC, there should be a bracket here, minus VUSV minimum minus VUSB, and that is actually coming as VUSB minus VUS minus VUSB. Okay, so now for this we have to design the shear reinforcement. It means we have to decide how many vertical legs we have to provide, what is the material of the shear reinforcement, what will the diameter of the stirrups, that we have to decide. It means we are designing actually the stirrups. Okay, so in the next step we have to calculate the spacing of the stirrups. For that we have to assume the diameter of the stirrups. Normally the diameter of the stirrups are assumed lesser than the main steel reinforcement diameter. So if you are normally it varies from 8 to 10 diameter. Okay, diameter of the stirrups. Then we have to decide the material also. Normally the material considered is mild steel. We do not provide the taut steel or twisted bar as a stirrup. Okay, they are always provided with a mild steel Fe 250 grade. And number of legs, as I discussed, either it will be 2-legged or 4-legged, that we have to decide according to our requirement. And then we calculate the spacing between the stirrups by using this formula. SV equal to 0.87 Fy S into ASV divided by VUSV into D. Now where it is given, clause 40.4, page number 73. So I will go again to the clause, IS code 40.4, this clause A, vertical stirrups. Okay, here, this formula. Okay, so shear reinforcement shall be provided to carry a shear equal to Vu minus tau CBD. The strength of the shear reinforcement shall be calculated as below. For vertical stirrups, it is calculated like this. Vus is equal to 0.87 Fy ASVD upon SV. So in this step, VUSV is already calculated. So the same formula, this formula is rewritten in the form of SV. So we have SV shifted to left hand side and VUSV to the right hand side, and we obtain this formula. So this formula gives us actually what is the spacing between the vertical stirrups. Okay. Now what are the limitations for these vertical stirrups? It is given here that the spacing between vertical stirrups should be less than 0.75 times D or 300 mm, whichever is less, where D is the effective depth of the beam. Where this is given, it is given on page number 47, again clause 26, 515. So I will move to page 47 now. Just let me check what is this page number. It is 86. Okay. Page number 47. Here. Okay. So here it is given the maximum spacing of shear reinforcement. The maximum spacing of shear reinforcement measured along the axis of member shall not exceed 0.75 D for vertical stirrups and D for inclined stirrups at 45 degree, where D is the effective depth of the section. Okay. And what is given over here under consideration. See, okay. In no case shall the spacing exceed 300 mm. Okay, so there are two clauses, 0.75 D or 300, whichever is greater. Sorry, whichever is lesser. Okay, it should not exceed 300 mm and it should not be, it should be less than either 0.75 D or 300 mm. Is it clear? ASV is actually the area of the shear reinforcement. It is calculated as again pi d square by 4 into n. N represents number of legs. How many legs are there? Whether it is 2-legged, 4-legged, etc. Now these number of legs are also indicated in the code through this diagram. Let me check that diagram. Let me show that diagram to you. Somewhere here I have seen. Yes. See here, these are the arrangement for different legs. Okay, so this is actually the multi-legged. This is also the multi-legged shear reinforcement. All these are the different ways of providing multi-leg transverse reinforcement. Okay, all right. So this is about the design for shear. Do you have any doubts in this? Design for shear. See, whenever we will start the problem based on this design for shear, you should be having all these steps with you. Okay, I don't think so that you have noted down all these steps, but I'm going to upload today's lecture material within 1 hour on VOLP, so that you will have the design steps for beams as well as design steps for shear reinforcement along with you. I request everybody to note down these steps in your notebook also, so that you will have these steps readily with you. When we solve the problems, you need to take reference of all these steps. Okay, without these steps you will not be able to solve the problems now. Okay, and the step by step procedure is not there in the code. No, any code gives any design steps. It provides only the specifications, only the limitations and the formulae up to certain extent. Okay, so whenever you want to design beam, slab, even column, the design steps should be known to you very well. Which should be the first step, which should be the second, third, like that. That flow of design should be known to you very clearly. Okay, so just I'm sharing all these notes on VOLP today. Just write down all these steps in your notebook and keep ready the steps with you for the next lecture. Any doubts in this?
No, ma'am.
Okay, so give me the attendance now. We will stop today, and in the next lecture, I'm going to consider the design steps for shear. We will consider first we will solve some problem based on design of shear reinforcement, and then we will move to the design of beams.